Alright, let me show you one example for this number 13. I would like to show you how I would attempt the problem number D. Here we need to find the error bound for the absolute error, and the only theorem that we study for the error term is just this guy. So this is the error term. And in the part D, you do see that n is 3, right? So therefore, we need to find the fourth derivative for this function. So for now, I define my f of x as cosine x plus sine x, and we need to find the fourth derivative. I just type in 4 primes here, and this is my fourth derivative, negative cosine x, actually cosine x plus sine x. So with that, I can now just go ahead and write my formula, write my error term for the this approximation. So my error term should be equal to here. This should be my fourth derivative at xi, and you do see that the fourth derivative is cosine of x plus sine of x, right? I just show you that in the Mathematica. However, you don't plug in x here, you plug in xi because this is xi, okay? Because of that. And on the bottom, it is n plus 1 factorial because n is 3 in this case, so it will be 4 factorial. And now let's continue to apply this formula. The error term here is going to be x minus x0. So my x0, x1, x2, x3, they're all given here. So which means x minus 0, x minus 0.25, x minus 0.5, and x minus 1.0. And I have to be careful that we have to be very clear that where's xi? Xi is in between the smallest node and the largest node. And where's x? X is the same in between the smallest node and largest node. So basically we have two jobs to do. One is to bound this guy using xi. The other one is to bound this guy for x. There are two different values. So now let's do the first one. To bound the first one, I can quickly take a look at the graph of the the fourth derivative, and where the xi is from 0 to 1. So basically, this is what I'm trying to look at using my graph. So I would like to run that, and seems to me this is where the maximum occurs. We need to figure out these points, right? So how do we figure this out? Basically, this function here is cosine xi plus sine xi, and to find the maximum of this guy, you need to find its critical point. That means you need to find its derivative, right? Find the derivative set to 0 and solve for xi. That's where the maximum will occur. Now, this is already the fourth derivative, and one extra derivative means the fifth derivative. Okay, so therefore basically I need to find the fifth derivative and solve the roots. Now, how can I do that? I hope that you now can take advantage of the all the roots finding techniques that you have learned. So basically here we just mentioned that we need to solve the find the critical value for this function. So find one more derivative for that, which is the sixth derivative. So here I'm gonna just make sure that I have, I'm sorry, the fifth derivative. So I just find one extra derivative. So the fifth derivative is cosine x minus sine x, right? Cosine x minus sine x. I want to find the roots for that. So this is my bisection method. In bisection method, I want to find the roots of cosine x minus sine of x. So I type in this function in my bisection method. Please do not get confused by this f and the f given here. This guy is, I want to solve the roots for this guy. This actually is already the fifth, the fourth derivative of my original function, right? So that's what I have. And my x0 is from x is from 0 to 1. So I would like to take a look at that. It seems to me that the 0 is right here. So in between 0 1. Now all I have to do is to type in the initial value. So let me make this bigger, much bigger. So my initial value is from 0 to 1. I can see that this should work because 1 is positive at 0 and at 1 it's negative. So I just run it, and my program tells me that let me take a look at my program here. Sorry about that. My program supposed to be the roots I look for is cosine x minus sine x. I did not update that, so this will be the updated one. So let's run that again. So what is p? P is 0.7853926. So let's get this down there. So I copied the solution here. So here xi I should use is this guy, right? So this is what my xi is supposed to be. Now I'm done with my bounding this guy. I'm done with bounding this guy. I just need to plug in xi into there. And now I need to bound this guy. So again, this is how do I bound this guy? How do I bound this guy? So how about for now, this is my say, let's call this as my g of x, okay, g of x, and I need to find g prime of x and set this to 0 and find the critical point, and then I will select the maximum from those critical points and the end point. So this is the procedure I would like to do. And again, there's another root finding problem here. I need to first find the g prime. So let's do that. So now I type in my this function. This is the function I want to maximize, right, from 0 to 1. So I'm gonna run it so that it looks to me the maximum occurs right here from the graph. And now this is somewhere between the 0.6 and 0.1. So I need to figure out what this x value is so that I can plug into my error term. So keep that in mind. Now I would like to make sure that so let's look for this one. And how do I find this point? I need to find the derivative of this function, right? The derivative of this function and set to 0. So the roots finding problem is actually I'm gonna say the I'm sorry, let me call this as my g, right? This is the g. Let's run that. So this is g. So the roots I would like to find is the g prime. So I'm gonna change this to my g prime of x. So what is my new in my I want to solve f of x equals 0, but what is my f in my program? It will be g prime. Sorry if that's confusing, but so basically what I'm trying to do is I call this as my g. So this is my g. This is my function g, and I call its derivative as f. So f is the g prime of this guy. Please again do not get confused by this f and the original f. They're two different things, right? So and the purpose is to solve this equation, set this to 0. So this is what I'm trying to find. Again, back to my bisection method. So I define my g right here, and my f prime is g prime. F is g prime, and I need to solve for that. And so, by the way, let me show you the plot. So g prime. Let me show you the derivative. So you do see that the critical point. This is the critical point. It's in between 0.6 and 1.0, and at 0.6 the derivative is negative. At 0 is positive. So I would like to change my initial point to 0.6 to 1, and I will run this program, and now I do find the critical value I need, which is this guy. So I'll get this to my copy this to the problem. So this is my this time this will be my x. So this value 0.8 something, this value will be the one will maximize this part. So now I'm able to just write my final answer now. So my final answer will be cosine of 0.78539. So keep enough decimal plus sine of the same value 0.7853976 divided by 4 factorial, which is 24, and times, now here I should use 0.8315857 minus 0, right? Times use this x value, 0.8315 and so on and so forth, minus 0.25 and 0.83 minus 0.5, and the very last one will be 0.83 minus 1. And don't forget the absolute value at the end. We are looking for the absolute value. And after the algebra, and which would be, so I use my Mathematica again, and here I if you can recall, this piece is the fourth derivative, right? So this is my fourth derivative at the first critical point, and this is how I would this is what I call my g. So I type in my g, and therefore this is my g of the second critical point divided by 4 factorial. At the end, my final answer is, so I do know that this is going to be less than or equal to 0.00159. So this is my error bound. Now, to recap. So basically, you have two pieces. One is to bound the derivative piece, which is this guy, right? Which is this guy. The second part is to bound this polynomial, so which is this guy. Just do it separately. You use technology whenever possible.